So because of that, there are some chocolates coming round. And you've got to have one. I can't eat it yet. Okay. So you just hang on to it. I'll hang on to mine. Purple sweets. The complementary colour is yellow. And I learned that because purple ones are my favourite. And by complementary colour I mean that the material that looks purple is actually absorbing yellow light, which I think is quite exciting. What did I do? Oh, here it is. Now I'm nearly ready. My name is Professor Sylvia Draper, and just relax. I won't be a moment. Energy drink, that's what I need. A bit like your Lucozade energy drink, except they fluoresce without UV light. This one uses UV light. Lovely. Anyway, fluorescent materials are interesting materials because they absorb light, and the light causes the molecules inside them to get excited. That happens to me frequently. I'm frequently getting excited. And then either I relax calmly in a radiationless sort of way and I calm down, or I fluoresce. And that's what molecules do. They can fluoresce by releasing their energy in a way that emits the light. It's light very similar to the light that they absorbed to get excited in the first place. But chemistry, which is what I hope you will all do if you come to Trinity. Who's seriously thinking about coming to Trinity? I have to do it every day. Excellent. Who's going to do chemistry? Not quite so good. Okay. And is that because the rest of you didn't do it at school? A few nods. Okay. Well, I'll convince you that without chemistry, science is kind of missing the bacon in the bacon and lettuce sandwich or the beef burger in the middle of the bun. You've got the kind of the physics and the maths, but you haven't got the bit that's practical in the middle. Or you've got the biology and the geography, so you understand what the planet's doing, but you don't understand it on a microscopic scale, why what's happening is happening. So I'm going to show you, about matter. And you are actually chemical beings. You're like a walking laboratory, and you're full of chemicals. And the world around us is made up of things that have mass, have weight. So anything with weight, including myself, has substantial weight. I, therefore, have plenty of chemistry in me. And this is the description of the small atom. Atom comes from the Greek word meaning uncuttable. This is what a solid looks like. In a solid, all the atoms are closely packed together. And all that can happen really when this molecule is solid sees some temperature or gets excited is a bit of vibration. And that's about it. This one stays in the corner. He doesn't go very far. However, this is the best bit of the whole lecture. Situation in a liquid, quite different. In liquid, things have room to flow. Started off the corner, could end up. The type of matter that we have on planet Earth is gas. But if I ate all of those, I'd have so much chemistry going on, I wouldn't be able to get upstairs. That's more or less the situation in this house. If everything with maths does some chemistry, and it's really important that we have some knowledge of chemistry, and it gets lost. So I'm going to show you a little bit that you should think about. This is life without chemistry. Life without chemistry would mean, for a beginning, you weren't here. It would mean that you couldn't breathe, because you wouldn't have little iron atoms in the middle of an octahedron flowing around your body, waiting for for oxygen to come in and sit on the iron and travel around your body to allow you to breathe. You would have no muscles, you wouldn't be able to breathe, you would be no water, and there would be none of these things, which you can see touch on medicine, they touch on pharmaceutical treatments, they touch on how to make new materials, things that do glow, that are smart, glasses that change colour in the sunlight and become transparent. None of these things. Environmental issues we're going to have a look at, and that touches on green chemistry. Chemistry sometimes is associated with chemicals which people think are bad, but chemistry is not bad. Chemistry is actually simply a description of the reactions that happen to every single material in the planet. And we can, with an understanding of chemistry, manipulate those materials so that we can do something useful with them. Now, I'll just show you that without some knowledge of chemistry, we would still be literally the planet apes. We would literally be, because without some knowledge of chemistry, we would not have developed as a species as we are now. If you look at the periodic table, it's no surprise that it travels from copper to titanium, goes iron, copper, and titanium. They're all transition metals, and our understanding of how we manipulate metals meant that we could make tools. We could make coins. Here is primitive man, you could say, although it's one of our first civilizations. And actually the colour of materials began to take on additional mystic or important meanings. For instance, blue in ancient Egyptian meant the colour of kings. And so how do you produce blue became an important issue. How do you coat the inside of your Egyptian tombs to ward off people that were thinking of somehow breaking into the life of the dead? Well, what you do, as Emperor Augustus told you, is you mix a bit of sand, some natron, which is a natural material, rub it together, get a fine powder, add some copper, sprinkle it with water, and stick it in an oven. There you go, and you've got blue. So suddenly, we can make blue. 12th dynasty, we were making pigments and paints. We were able to take limestone, sand, and copper carbonates, which is malachite, raw materials, dig them out of the ground, and turn them into something useful. And mankind has been doing that ever since. The development of mankind also means that we have an understanding of how to make materials. What is the mixture? What's the ratio of things that allow you to make a specific product? And one of the things that we learned how to make was this guy, Francis Roger Bacon, in 1242, long after the Chinese had been doing it for ages, worked out what the mixtures are that you need to make gunpowder. And you need oxygen, because you want something to ignite, and you need some carbon, and you need some sulfur. And the combination of those three things allows you to make gunpowder. Not perfect, because sometimes it would explode in the operator's face. And if you got the mixtures wrong, or if you got the powders wet, you were also in trouble. I'm going to show you about fireworks, which kind of relates to gunpowder here. And I'm going to show you that years ago, we used to use the colour of a material when it burns. I am very badly looking for my fire. Put it in a sensible place. We used to use the colour of materials when they burn to identify them. So I'm going to show you. Probably set fire to the place. This is one material, and when this one burns, it creates a really vivid white flame. This material is magnesium. Has anybody burned magnesium? Cool. So this is magnesium. That bright white flame is characteristic of magnesium, and what's happening is that the electrons in those metal atoms are getting excited by the flame, and as the electrons relax back down, you can create different colours. So this is a different metal. This is copper. Okay? And I won't do that one because that one seems to be green as well. This is just like you would have. Whoa! Once I set fire to the bench. I better just move this box. And just like the top of, you know your Christmas pudding? When you set fire to the ethanol on the Christmas pudding, if you put a little bit of salt in, I know probably the Christmas pudding will taste a bit salty, but the flame will be yellow, yellowy orange. Much more exciting. And this is lithium. So I stopped there, but can you see how they gave us different colours, and the different colours are telling you something about the electrons in the atom and where those electrons are held. And that tells you that electrons are the species that give rise to atoms reacting in a flame. So I'm going to turn this off now, as far as I remember. I don't need it again. Now I'm going to show you some chemical problems that we've helped to sort out. No, I won't. Not that. I'll do this. Survival was the main objective of primitive man, and even today I'm going to explain to you by the end of the lecture why survival should be your primary motive to get through to the next generation of people on this planet. How did primitive man survive? Well, you can strangle a kangaroo if you're able to catch it. You could wrestle an elephant, I guess, and try somehow to pull it to the ground, or you could poison it. Then it'll drop down dead without all the effort. And that's what, even today, Malaysian people do. They have blowpipes. They take a plant, extract the poison from the plant, it's called strychnine. They use the tooth of a large guinea pig-like animal as the scope, and they have, now you must remember to blow, not suck. And you blow, and out of the dart, the end of the dart, comes a tiny little, very fragile stick. And that fragile stick on the end of it has a poison. That poison, strychnine, is very cleverly used. They know what dose to apply, which animals it's effective on. They change poison depending on the animal. They change dose. And you have to think about it. It has to be that when the animal drops to the ground, you and I can eat it without it poisoning us. So they've learnt about dose specification and host specification. And this was primitive man. We can assume that you and I, our ancestors, did the same thing. All other interesting things that we developed very, very early on was how to produce alcohol. That was a major achievement, just a little bit, around 200 BC. Again, taking and fermenting materials, fruits, was an interesting survival, I suppose, procedure. Now, strychnine has been, probably you've heard of strychnine. Strychnine is a quite nasty poison, and chemistry is everywhere. It's even in the literature. If you're an Agatha Christie fan, you'll know about arsenic and lace. You'll know about sharing omelettes between the victim and the murderer. And the victim dies because the murderer has built up his immunity to the poison. Well, strychnine in history has been used many times. In fact, it was used in Henry VI's time, I think. And poisoning kings used to actually have tasters to make sure they didn't fall foul of this. Well, if you wanted to feed somebody strychnine, you'd have to be a little bit careful. Strychnine has a horrible bitter taste. So what you do is you administer it in jelly. Something sweet tasting. And one lovely man called Thomas Wainwright found himself in serious difficulties financially, and he managed to, through an artistic temperament, basically to spend all of the money that the family had. A little bit like the previous government and the one preceding. But his uncle was very rich, and so he decided that he would poison off a few of his relatives and increase the his proportion of the inheritance. So he fed Helen, his younger sister's, his wife of his younger sister, with strychnine and jelly. It was supposed to be a cure after she'd suffered some sort of ME-type symptoms. And sure enough, she died of painful convulsions, and Linden House came sort of on the market. So it's everywhere. It's in our bones, in our survival, and in our history. Let me just show you where else. These poor ladies, notice how it's the poor ladies that get the grotty jobs, but I think and probably half the men have been killed off. But anyway, these are metal vats, and what they're doing is they're producing sulfuric acid, and sulfuric acid is a really important raw material for many of our sort of modern materials. And so what they discovered, if you use a metal vat, your production of sulfuric acid improved hugely. We were also using that very fact in kitchens all around the country, because if you use a copper bowl to whisk eggs, they whisk more quickly. So when you want to whisk eggs, make sure you use the metal whisking units, not one of these, silicone Teflon-y things. You'll be there forever. Metals catalyze reactions. And they discovered this, and this is a form of what we call heterogeneous catalysis. This is the metal layer, and in come the reactant chemicals, and somehow when they hit the metal surface, the metal surface ignites properties that were asleep. That was the original definition of catalysis. It awakes properties that were asleep and allows the reactants to make products. Lovely reaction, because you can remove the products very cleanly, because the reactants come in and the products come out. However, it's an inefficient process, because buried under this metal surface are all these metal atoms that you can't get at. So they're there, potentially useful, but actually useless, because the reactant can't hit them. And if I just explain how inefficient that is, here's my catalytic surface, and below there were lots and lots of other Ferrero Rocher chocolates. You'll have to believe me. And I'm only left with the metal surface, but underneath are all these useless atoms that we can't get at. And as the reactant molecule comes in, it has to hit a specific place on the surface. Missed. Now actually, missed. It's supposed to take only about 1 in every 8 billion manages to hit the surface in the right place. And I don't really want to be here for 8 million attempts. I did it. Okay, so that's inefficient. So what we do, there's good things and bad things about this process. We have a reactive metal surface, we can get the product off, but it's rather inefficient. This is a chemist's delight. This is the sort of solution that we come up with. Just to prove it to you, how does the metal surface work? Well, this was generated by what's called an electron microscope. And what it does is it has a very pointy little needle that runs across the surface, and it produces an electric, it has a voltage going through it, and we pass it across, and depending on the conductivity of the material below, it creates a pattern, surface pattern, topological pattern of the surface. So these are all my surface atoms. See them all? And here's an oxygen molecule that's come in, and when it's hit the surface, you can see that the oxygen molecule has split. So this surface has activated the breaking of that bond, which means those reactive oxygen atoms can go on and do some chemistry. Well, the problem is that this is not particularly efficient, so how can we speed it? Well, I'll tell you what we'll do. We'll put the catalyst into solution. The catalyst are these red atoms. Now, Mr. Catalyst, you can hit as many reactants as you like, and you can produce lots of green products. Problem is now, we've got the green guys and the blue guys mixed together, and the catalyst. Everything is all jumbled up. Probably super efficient, but how are we going to get the product out? What will we do? I tell you what we'll do. We'll create a honeycomb. We'll create a Malteser-like species. Because inside the Malteser we can attach our catalyst, through the honeycomb, it will react, and out the other side will come the product. But the catalyst won't come with it. We'll end up with a product that's clean. This kind of solutions to major problems has resulted in some enormous advances in technology in the last 50 years. Just some of them I put on the screen, from the way in which materials interact with the body, right through to cloning and nanotechnology. Let me talk to you a little bit about nanotechnology. Nanotechnology is basically chemistry at the nanoscale, which is a billionth of a hair, 1 × 10⁻⁹ meters. This is the old computers that we would have needed to create the same function as your mobile phone. This is the old technology for producing sound. This is what we have now. And this is the old laboratories that have been replaced, in theory, by reactions on a single chip. It's simply the application of problem solving that gives chemists the edge, which allow us to contribute to all of these developments. Now, we have some serious issues that are still to be dealt with. One of them is that this planet is going to run out of energy. And so will I, fairly shortly. And the reason it's going to run out of energy is because we have one primary source of energy, which is oil and coal, basically oil. And this problem has become so vast that actually it will hit, possibly you'll survive, but it'll be your children. So we're only 1 generation away from this being a major catastrophe. When you burn carbon-containing fuels, they produce a lot of carbon dioxide, and carbon dioxide acts as a blanket around the planet and makes the planet get warmer and warmer and warmer. And as it gets hotter, the ice caps will melt, and they'll get to a point where we can't get it cold enough again to refreeze them. The amount of carbon dioxide in the atmosphere in 50 years' time will be 3% higher than now. This is a prediction. And that was only hit 50 million years ago, when basically Ireland was a mango swamp. So that's the kind of lifestyle you'll be living in 50 to 70 years' time, unless we train you to solve this problem. We need more efficient production of chemicals we need less waste, and primarily we need a new energy source. And one of those might be to power cars by hydrogen, because hydrogen, when you burn it, creates water, which has none of these serious environmental consequences. I talked a little bit about chemistry on the nanoscale, and I'll just tell you a little bit about it now, because the School of Chemistry here in Trinity is currently ranked 36 in the QS rankings in the world. It's one of the best places, well, one of the top 36 places in which to study chemistry, and the best in Ireland. And one of the reasons for it is not just because we've looked at energy as a problem and a solution that we're trying to come up with, but also because we've looked at the chemistry that occurs on the micro scale. It's called the nanoscale, and it's actually about the size of a molecule, or 1/80th of the diameter of a human hair. And we can now we can switch molecules on and off. We can make them open like gates. We can make them scuttle to and fro in order to produce, if you like, a molecular conveyor belt, a sort of an industry, a manufacturing plant on the micro scale. And these are things that all of us need to consider in order to make sure that mankind survives. This is a picture of DNA, and DNA is also on this nanoscale, and DNA has a right-handed twist. It's remarkable, really, because the base pairs of DNA could have twisted in such a way as to give you left-handed or right-handed twists. Those are 50-50 chances. And yet 99.9% of life on Earth has a right-handed twist. And with a right-handed twist, you have to think very carefully about where molecules might interact with DNA. And so these medicinal materials that affect the way in which DNA replicates, particularly nasty ones, cancer-containing ones, have a twist. So now you can eat your sweet. And when you eat your sweet, you have to twist it. You undo the helix, effectively, of the DNA in a kind of a mythological sense. So I'm going to, I hope now that I've given you some feel for why you should do chemistry. If you're considering science at all, really seriously think about taking chemistry in their first year, and with it, I hope that those skills will allow you to make a difference in the next generation. And the last thing I wanted to do was to make a bang, because I always believe you should finish with a bang. And so, I have a small amount of methanol, and all I need is a target. So, something, perfect. There's always one. No, you can just go stay exactly where you are, perfect. If you'd like to stand up, that would be even better. So all I've done is I've put a little bit of methanol in this, and now I'll tell you what I call the experiment. I call it methanol gun. All I'm going to do now is you just stand perfectly still, and I'm going to try and shoot you. And, you know, there's a limit to how many people we can let into Trinity. And I have to find ways to reduce the number each year. And it's entirely your own fault if I manage to hit you. But I can assure you that I've never managed to hit anybody yet. But people near you are probably more. Did you want to shoot it? Just come down, you do it. Oh, super. And if it doesn't work, I can blame you. So, all I want you to do, has anyone seen the liquid nitrogen trick before? Anybody got baristas and quartz? Lining up? No? Going to move from water treatment? No? Never mind. I don't understand. I'm a doctor. Now. Hear that noise?
Yeah.
Don't touch the end.
Okay.
And all you've got to do to earth it. Oh gosh, I have such great fun. All you've got to do, right, is switch that on, put it on the screw, and what will happen is a little arc will travel from one nail to the other, and it should blow the cork out the top of the methanol gun, and I'm hoping that I'll hit the person instead of the projector. Well, I think of course, you're utterly responsible for. Do you want goggles? Okay, I'll stand well back. Don't mind me. Hold on. Perfect. Absolutely. As a small as we had I don't understand for the wart treatment. He's going to smash some rubber tubing for me instead. So, I think for this we will put on goggles, just in case. Oh yes, I have it. Excellent, now he looks there. All you have to do is, don't touch the very end because it'll be at minus 190. I think. Anyway, not really that serious, but it will burn easily, frostbite.
Okay.
And then just lift it up, put it down there, and smash that end. The atoms got so cold, they're now very brittle. brilliant, isn't he? Whose friend is this? Is anybody... that probably do. Brilliant. So thank you very much. Thank you. Okay,